Welcome to the Explainer. So today, we're looking at something that, honestly, just fundamentally rewrites the rules of how large language models generate text. If you've been working with LLMs for a while, you know the drill, right? It's a very specific, pretty rigid process. But today, we're diving into a radical new model architecture that completely shatters that old mold. We're talking about DiffusionGemma, and we'll see exactly how it was brilliantly integrated into vLLM. I want you to just think about this for a second. What if an LLM didn't write word by word, left to right, but instead just generated entire paragraphs all at once? I mean, standard autoregressive models, they're basically like hyperfast typewriters. But what if we replace that typewriter with a painter's canvas?
Well, that brings us to this absolutely staggering number, 1,288. That is the number of generation tokens per second they're hitting on an H200 GPU with this new architecture. Let me put that into perspective. We're talking about speeds up to 6 times faster than your standard baseline. Literally 6 times. So how is that even possible?
Okay, let's dive right into this. Here's our roadmap for today. 1. Autoregressive versus block diffusion. 2. The DiffusionGemma architecture itself. 3. The denoising loop explained. 4. Tricking vLLM's architecture. 5. Mastering dynamic causal attention. And finally 6. That awesome 6 times speed up. Starting off with section 1, autoregressive versus block diffusion. Let's actually establish the core problem we're trying to solve here by comparing these two generation paradigms. With our traditional autoregressive model, text is generated sequentially, right? Just a single token at a time. And the major bottleneck here is memory bandwidth, because you've got to move massive model weights through memory for every single token you generate. It's incredibly heavy. Now contrast that with block diffusion. Instead of going sequentially, it uses a 256-token canvas, essentially refining all 256 tokens in parallel at the exact same time. This is a real game changer because it brilliantly shifts the bottleneck. It trades that heavy memory bandwidth pressure for additional compute. And, at low batch sizes where you've got spare compute just sitting there, this is an incredibly attractive trade-off. It unlocks insanely low latency responses.
Moving right along to section 2, the DiffusionGemma architecture. Let's pop the hood and see what's physically powering this completely new approach.
So, surprisingly, it's actually a very familiar foundation. DiffusionGemma is a 26 billion parameter discrete diffusion language model, but it's built directly on the standard Gemma 4 backbone. The radical part here, it isn't the weights themselves, it's entirely about how those weights are utilized to actually produce the output. Right, so it actually runs that single set of layers in 2 very distinct modes. First up is the encoder mode. This acts exactly like the models you already know. It uses causal attention, which just means tokens only look backward, and it writes directly to the KV cache. It runs twice per block, once to pre-fill the prompt, and then once at the very end to kind of commit the finished block. But then we have the decoder mode. This is our denoising mode. It uses bidirectional attention. This means every single position in that 256-token canvas can look at every other position, refining the whole block all at once. And here's the crucial part. It only reads from the KV cache during this phase. It does not write to it yet. Okay, so how does that refinement actually happen? That brings us to section 3, the denoising loop explained. Let's walk through the actual step-by-step process. Here is exactly how a 256-token block goes from just pure random noise to a perfectly finished paragraph. Step 1, prefill. The model prefills the prompt using that encoder mode we talked about. Step 2, denoise. The model basically runs multiple passes over a noisy canvas, denoising it bidirectionally. Every single position samples a candidate token. Then, once things stabilize, we hit step 3, commit. The model switches back to encoder mode, commits the clean argmax prediction, and boom, emits the entire block all at once. But you might be wondering, how does it actually decide which tokens to keep along the way? Well, it uses a really clever trick called entropy-bound denoising. Think of it kind of like a confidence budget. Low entropy means high confidence, so it accepts only the most confident positions, and these sort of become anchors. The uncertain positions, those get thrown out and replaced with fresh random tokens. Over a few steps, those confident anchors start propagating context to their neighbors, so the picture literally snaps into focus as more and more positions fall under that entropy budget, until eventually the whole canvas has converged. To speed this whole process up, the architecture uses something called self-conditioning, and this brilliantly illustrates why the model doesn't actually have to start from scratch on those rejected tokens. Instead of just passing hard tokens back into the loop, it takes the full softmax distribution from the previous step, converts it into a probability-weighted average of token embeddings, and then feeds that directly back into the canvas. Essentially, it's giving the model a memory of its own last belief. So even if a position is renoised, it carries forward a little hint of what the model was leaning toward on its last pass.
All right, let's get into the engineering. Section 4, Tricking vLLM's Architecture. Let's look at how they actually made this work using speculative decoding.
The engineers at Google DeepMind and vLLM came up with an absolutely brilliant hack for this. I honestly like to think of it as a Trojan horse. They disguised the entire diffusion process by essentially reusing vLLM's existing speculative decoding data path. Now, in standard speculative decoding, a smaller model proposes a bunch of draft tokens, and the main model either accepts or rejects them. For DiffusionGemma, they simply tell vLLM to treat the entire 256-token canvas as a giant set of draft tokens. These tokens are just going to be entirely rejected over and over until the whole block converges, at which point they are all fully accepted.
Now, what's really interesting about this is how they made that Trojan horse work. They used the new ModelState interface. So instead of forking vLLM entirely, models can now define custom hooks for their specific needs, while keeping the core model runner completely generic. So you have prepare_inputs, which handles embedding the canvas in that cool self-conditioning math we just talked about. Then prepare_at10 toggles between the causal and bidirectional attention modes. And custom_sampler swaps in the specific logic for accepting and rejecting the canvas tokens. It is an incredibly clean abstraction.
In that custom diffusion sampler, it essentially lies to the system to pull this off. During the denoise phase, it tells the scheduler that literally all tokens are rejected. This is vital, actually. It completely freezes the KV cache from advancing. It forces the scheduler to just keep the sequence exactly where it is and run the exact same block again on the very next step. Only when the canvas is fully converged does it finally hit commit, suddenly claiming, hey, all 256 tokens are sampled, finalizing the entire block.
Let's keep moving. Section 5, Mastering Dynamic Causal Attention. We've got to tackle the massive challenge of per-sequence causality.
So, in a real production environment, to keep latency low, vLLM batches multiple user requests together, right? But with DiffusionGemma, you run into an issue. You might have request A over here in the causal prefill stage and request B in the bidirectional denoising stage. Previously, causality was a batch-wide property. It was all or nothing. To fix this, they introduced dynamic per-sequence causal attention, which is now supported in Triton and Flash Attention 4. This dynamically adapts the attention mask on a per-request basis, all inside the same forward pass. So the prefill request masks out future tokens to save compute, while the denoise request right next to it is fully allowed to look in all directions.
In this dynamic approach, it also extends to sliding window attention. In your standard causal models, a sliding window only looks backwards. But for a denoising canvas token, the window dynamically expands to become symmetric. It attends to an equal number of tokens before and after its position. The software has been upgraded to gracefully handle both one-sided and symmetric windows simultaneously in the exact same batch. Talk about engineering elegance.
Finally, we've made it to Section 6, the 6 times speedup. Let's look at the actual throughput results of trading that memory bandwidth for compute.
So, the crucial point here is that the ultimate payoff is absolutely massive. By generating 256 tokens at a time, this FP8 diffusion model operates at roughly 6 times the speed of a standard autoregressive baseline. Let me break down these numbers for you. On a single H100 GPU, it generates 1,008 tokens per second. And on an H200, it reaches an unbelievable 1,288 tokens per second. The latency benefits here, especially for interactive applications, are just completely off the charts.
And the best part? You don't even have to wait to try this out. Fully quantized checkpoints of the 26 billion parameter model are available right now. You can run it in FP8 with dynamic activations, or push it even further with NVFV4, where both weights and activations are quantized. And if you're worried about quality drops, don't be. Evaluations on really tough benchmarks like ME 2025 and GPQA Diamond show that it fully maintains its proven accuracy, despite using an entirely new generation paradigm.
Which really just leaves us with one final thought. We are literally watching the underlying mechanics of AI generation evolve right in front of us. As low-latency block generation transforms LLMs from these rigid typewriters to dynamic parallel canvases,
completely breaking the memory bandwidth bottleneck in the process. What will you build with all this newly unlocked compute? I really hope this explainer gave you a clear picture of how DiffusionGemma works under the hood. Thanks so much for diving in with me today, and keep exploring.